Thank you for joining us on Synthesis Workshop. In today's installment of our Advanced Organic Chemistry course, we're joined by Dr. Tracy Liu. Tracy earned her bachelor's in chemistry from UC Berkeley, where she did undergraduate research in the TOST group. She subsequently earned her PhD at Princeton, where she worked in the MacMillan group, as well as a master's in art conservation from the University of Delaware. She has a very unique career profile, with work experience at the Rijksmuseum in Amsterdam, as well as the University of Delaware, where she's taught about the intersection of science and art conservation. Currently, she's a scientist in the Discovery Process Research Group of Janssen in Belgium. Today, as we continue our Special Topics and New Technologies module, Tracy will give us a lecture on Photoredox Catalysis. And from there, I'll let you get started, Tracy. Thank you very much for joining us as a guest speaker today.
Hi, thank you for the introduction, Matt, and welcome everyone to another installment of the Synthesis Workshop Advanced Graduate course. As Matt said, my name is Tracy. I'm currently a scientist in the Discovery Process Research Group at Janssen Pharmaceutica, based in Belgium. And I got my PhD in 2017 with Dave MacMillan, where part of my work focused on developing a photoredox catalyzed method for the site-selective functionalization of peptides and proteins. Photoredox catalysis is the topic of the lecture today. It's a type of chemistry that's been around for quite some time, but in the last 15 years or so has really taken root as a powerful synthetic tool, and hence why it's worthy of a special topic lecture. I'm going to turn my video off so nothing obstructs the screen, but I hope you enjoy the lecture and I hope you find it useful. These three reactions shown here can be thought of as the pioneering three that kicked off the modern era of photoredox chemistry applied to synthetically enabling methodology development. A 2+2 cycloaddition from Yoon, an asymmetric alpha alkylation of aldehydes from Dave MacMillan, and finally a debromination of alkaloids from Corey Stephenson. This last example from the Stephenson group will be shown in greater detail later in the lecture. Photoredox catalysis has enabled chemists to make a wide variety of bonds, CC, CN, CO, carbon halogen, and all doing so under mild conditions, meaning low temperatures, avoiding the use of highly reactive radical initiators, and often using visible light as opposed to ultraviolet as the energy source for the reaction. Finally, another shared characteristic is the often extremely low catalyst loadings. Loadings around 1 mol% or less are quite typical. Its synthetic utility is now well established, but what is photoredox catalysis? To start, let's backtrack to a broader term, photochemistry, which is an umbrella term that includes electron transfer, which is photoredox catalysis, as well as energy transfer processes. There are other types under the photochemical umbrella, but these two are the largest subcategories. And there can be many definitions of photoredox catalysis. However, for this lecture, I will use the following definition. Photoredox catalysis is the chemoselective generation of a radical species via the absorption of visible and occasionally UV light by a chromophore, resulting in productive single electron transfer processes with organic substrates to form synthetically useful products. So now that we have a general definition down, let's look at the outline of this course. In the first section, we'll go through some basics, looking at catalyst classes, understanding excited state photophysics, understanding that there are two mechanisms of excited state catalyst quenching, oxidative and reductive, and that there are different types of transformations, net reducing, net oxidizing, and redox neutral. From the basics, we will move into the next step in complexity, which is to be able to become fluent in understanding multi-catalytic or multi-component photoredox reactions. This is the section that will really demonstrate the synthetic power of photoredox catalysis, the fact that it can be synergistically coupled with multiple other forms of catalysis that are each very powerful in their own right. This section is meant for newcomers to photoredox catalysis to be able to understand what is going on when they read the current literature and understand complex mechanistic cycles that may comprise up to 3 concurrent cycles. Finally, this last section is geared towards the ultimate in understanding, which is the ability to design your own novel photoredox-based transformation. Knowing how to choose the right photocatalyst, understanding how you can complete the catalytic cycle via substrate choice or the need for additional additives, understanding how you can tell what mechanistic pathway may or may not be occurring, and going through some common troubleshooting and some practicalities of the reaction setup. And then we will conclude with just one final slide where I've picked a few current trends in the field today. We start with the 3 basic classes of photocatalysts, the ruthenium and iridium polypyridine photocatalysts and the organic photocatalysts. These are the most commonly seen catalysts in the literature, though, as you will see on the last slide, one of the current trends is to explore other metal-based photocatalysts. With the ruthenium and iridium photocatalysts, they can be decorated with various ligands, which will impact their redox properties. And with the organic photocatalysts, there are many classes: flavins, berylliums, benzophenones, etc. The review listed here will provide a good source of information about the various kinds. But regardless of the type of photocatalyst, they will all share some key common characteristics, which are having long excited state lifetimes, important because the excited state photocatalyst needs to exist long enough that it and the reactive substrate can diffuse towards each other and engage in a productive bimolecular electron transfer event over competitive deactivation pathways. Actually, photocatalysts with sub-nanosecond excited state lifetimes can relax back down to the ground state before it can diffuse to and react with a substrate. Secondly, they should also ideally have high quantum efficiencies for formation of the excited state. You want this value to be as close to unity as possible. The excited states of typical ruthenium and iridium metal polypyryl complexes are formed with near 100% quantum efficiency. And finally, they should ideally absorb in the visible region, since this is usually orthogonal to the absorption of small molecules that will likely be your substrate. Now we move on to what the excited state photocatalyst looks like and how it reacts. For this, I'm going to use the ruthenium tris bipyridyl or RuBiPi photocatalyst as an example. And shown here is a simplified molecular orbital diagram of its ground state. Upon excitation with visible light, blue light being best, an electron from the metal-based T2G orbital will be excited to a ligand-based pi star orbital in a process known as metal-to-ligand charge transfer, or MLCT. This will initially give rise to a singlet excited state, which is shown here. The initial singlet excited state will then undergo a rapid and thermodynamically downhill process called intersystem crossing, wherein the initially excited electron will spin flip to arrive at a triplet excited state. This triplet excited state is long-lived because relaxation to a singlet ground state is spin forbidden. This long-lived triplet excited state is a key property to a good photocatalyst for synthetic chemistry. Jablonski diagrams are powerful tools used to visualize the various electronic transitions that can occur to a photoexcited species. Here on this diagram, only some of the many possible electronic transitions are shown, with major ones being absorption, internal conversion, intersystem crossing, fluorescence, and phosphorescence. The gray lines represent different vibrational energy states. As an aside, another way of visualizing electronic transitions, which is technically more accurate than MO diagrams, is to use potential energy surface diagrams, like these shown here. Either way, once in the excited state, you can effectively think of the metal as having been oxidized and the ligand reduced, hence why on the far right they are drawn conceptually as ruthenium being in its +3 oxidation state with a radical anion on the BiPi ligand, basically making the metal a strong oxidant and the ligand a strong reductant. This is what is responsible for giving the excited state its dual nature. Focusing in on this dual nature, you will see that this is what is responsible for the two quenching pathways that are characteristic of photoredox catalysts. First, we will focus on the reductive quenching pathway. This pathway is defined as when the excited state photocatalyst is reduced. Thus, it leverages the strongly oxidizing nature of the metal center. In the simplified MO diagram at right, I'm going to now rewrite the ruthenium oxidation state as being in its 2+ state, since this is technically its actual oxidation state. But remember that it effectively behaves as if it's in its 3+ state. This is manifested by the fact that there is a hole or missing electron in the metal T2G orbital, shown here. Compared to the ground state catalyst, this represents a LUMO-lowered orbital for accepting an electron from a donor substrate, shown here in orange. Once having undergone this reductive quench, the photocatalyst will now be in a ruthenium-1 ground state, and a final donation of the electron from this pi star orbital to an acceptor substrate will return the photocatalyst to its original ruthenium-2 ground state. Now for the other potential mechanism of quenching, the oxidative quench, I'm bringing back this conceptual depiction of the RuBiPi excited state. So metal in a 3+ oxidation state and the ligand reduced, in order to remind you of the reduced ligand part. Oxidative quenching is defined as when the excited state photocatalyst is oxidized, meaning it gives up an electron, which leverages the strongly reducing nature of the ligand center. this ligand is strongly reducing due to the HOMO-raised electron shown here. Thus, in the presence of an acceptor substrate, this electron will be donated, thus oxidizing the excited state to a ruthenium-3 ground state, which can be recycled back to its ruthenium-2 ground state by accepting an electron from a donor species, shown in orange here. While we use the Rubippi photocatalyst in this example, such oxidative and reductive quenching cycles are characteristic of most photocatalysts in general. Exactly which of the two quenching mechanisms prevails in a given reaction is going to depend on the substrates and reactants that are present. In the subsequent slides, this concept will be illustrated through specific examples. But at this point, it's also time to mention how one gauges just how oxidizing or reducing an excited state photocatalyst is. And this is done using a unit of measure termed reduction potentials, which is the term symbolized by an E here at the top of this equation. E is related to the Gibbs free energy by Faraday's constant, the F term. Thus, simply put, reduction potentials reflect the thermodynamic favorability of a process to undergo a single electron reduction or oxidation event. Reduction potentials are something that are empirically measured for each species. You're essentially measuring the tendency of a solution which has your substrate or species of interest dissolved in it to either give or take an electron from a reference electrode. The most common reference electrodes used is the saturated calomel electrode, or SCE. Now, reduction potentials can be confusing because though called reduction, they're also used to refer to oxidation half reactions. And this is simply due to a convention to write all electrochemical half reactions as reductions. So for a reduction event, this is straightforward. The reaction is written in the forward direction as a reduction, and the reduction potential, or E1 half red, will be some value that's usually going to be negative. This is because in the ground state, it's usually not thermodynamically downhill to have a single electron reduction of a neutral species. Note that next to the E1 half red, in parentheses, you have the reactant product notation. So here that's A to A radical anion. Now for an oxidation event, the top line shows the half reaction written as an oxidation. However, as I mentioned, convention dictates that they always be written in terms of a reduction. So we flip the half equation, giving us the second line. As a result, the oxidation potential, or E-ox, is still written as E1 half red. Even though everything will be written as a reduction potential, you can still easily tell which is a reduction potential and which is an oxidation potential based on the value. Oxidation potentials are generally going to be positive versus SCE. This is because it's thermodynamically favorable to go from a charged species to a neutral one. As the chart shows at the bottom, the more negative the reduction potential, the more strongly reducing it is, and the more positive the oxidation potential, the more oxidizing it is. As we go through various examples now to understand if a reduction or oxidation event is thermodynamically favored, just compare the values of their reduction or oxidation potentials. For reduction, the more negative species will be the one that reduces the other. And for oxidation, the more positive species will be the one that oxidizes the other. Now that we've explained the primer on redox potentials, let's look at some examples of reductive and oxidative quenching. Sticking with the Rubippi photocatalyst that you just saw, this is Corey Stephenson's seminal reductive dehalogenation reaction. I'm going to use this reaction to illustrate Rubippi in action in a reductive quenching pathway, as well as illustrate a second concept, a net reductive reaction. Looking at the mechanism stepwise, from the excited state Rubippi photocatalyst, in the presence of an electron-rich substrate such as Hünig's base here, the photocatalyst undergoes reductive quenching, oxidizing Hünig's base, accepting an electron in the process to give reduced Rubippi photocatalyst and the radical cation of the amine. You can see based off of the oxidation potentials here that the single electron transfer is thermodynamically favored since the excited state ruthenium's oxidation potential is actually more positive than that of Hünig's base. Now we have a highly reducing Rubippi 1 ground state photocatalyst, which will reduce the bromoalkaloid substrate to recycle the photocatalyst back to its ruthenium 2 ground state while furnishing a bromine anion and a carbon-centered radical, which is set up to undergo a hydrogen atom transfer or HAT event. Specifically, this species is presumed to abstract a hydrogen from the alpha position of the oxidized Hünig's base that was generated in the reductive quenching event. And this is going to furnish the dehalogenated product as well as this aminium, which is then going to be reduced by Hansch ester. Hansch ester in this case is acting as a sacrificial reductant, which is defined as a species that will be oxidized. and this is needed because the reaction is overall net reductive. So all net reductive reactions will require some sacrificial reductant in order to balance the electrons. Now, using the same Rubippi photocatalyst, I've selected another example, again from the Stephenson lab, where the mechanism goes by an oxidative quenching pathway. Moreover, this example also highlights a net oxidative reaction, which means that it requires a sacrificial oxidant this time to balance the electron count. Here, photoredox catalysis is used to oxidize tetrahydroisoquinolones to their iminium counterparts, which are then trapped by nucleophiles. Again, starting from the Rubippi excited state, this time in the presence of bromotrichloromethane, an electron acceptor, the photocatalyst will be oxidatively quenched, giving up an electron to furnish trichloromethane radical as well as bromine anion and the oxidized Rubippi-3 ground state catalyst. In the presence of the tetrahydroisoquinoline substrate, an electron-rich donor amine, the ruthenium-3 oxidized photocatalyst is then going to accept an electron, returning it to its ruthenium-2 ground state, and oxidizing the amine to its radical cation. Similarly to the first example, the two reactive intermediates now merge, wherein the trichloromethane radical is going to abstract the alpha proton of the tetrahydroisoquinoline radical cation to furnish the key reactive iminium substrate, as well as trichloromethane. In this case, the reaction is net oxidative. A stoichiometric sacrificial oxidant, defined as the species that gets reduced, is going to be needed. And in this case, that species is bromotrichloromethane. As an important note, in this example and in the last, you saw net reductive and net oxidative examples respectively, but there are also redox neutral examples, where no sacrificial reductants or oxidants will be needed, but these will be shown in subsequent examples. Both examples just shown were single catalytic reactions, namely only involving a photoredox catalytic cycle. With the basics down, we can now turn our attention to multi-catalytic or multi-component reactions. As already mentioned, this section will demonstrate the power and agility of photoredox chemistry to form a truly diverse range of bond connections. And the crux of this power lies in the fact that it can be coupled with other forms of catalysis, such as organocatalysis and transition metal catalysis, allowing one to leverage the unique reactivity advantages of each. The latter in particular has proven quite transformational and is thus going to be a major focus of this section. As the name implies, metallophotoredox catalysis involves the merger of photoredox and transition metal catalysis. Since this is a rather new field, the exact mechanisms of these reactions for both CC and C heteroatom bond formation are still being studied and understood. But in a very general sense, for CC bond-forming reactions, they will often involve one coupling partner, R1, that gets onto the metal, for example via oxidative addition, followed by a second coupling partner, R dot, that adds to this metal complex, oxidizing it in the process, and then this is being followed by a reductive elimination event that forges the key bond. Importantly, this R dot is typically generated in the photoredox catalytic cycle, either directly or via radical activator, which we will see an example of for both very shortly. The exact order of the steps and the way in which the photocatalyst and transition metal cycles interact is an ongoing area of research, but the important thing to understand is that formation of an alkyl or aryl radical is an important part of the metallophotoredox process. So before going into specific examples, I thought I'd show some organic radical precursors as well as their feedstocks. Carboxylic acids will furnish alkyl or aryl radicals after oxidation and loss of carbon dioxide. CH abstraction from an aldehyde can furnish acyl radicals. Alcohols can be activated via engagement with an N-heterocyclic carbene or by covalent activation through an oxalate or xanthate, just to name a few. The selected examples coming up will showcase how these four functional groups will provide access to the key radical intermediate in metallophotoredox reactions. For the rest, the two reviews listed at the bottom here will showcase all of the radical precursors listed on this slide. Additionally, the upcoming slides will only have examples of nickel photoredox catalysis, the metal that is most widely used in metallophotoredox. However, it should be noted that other transition metals, such as palladium and gold, were already coupled with photoredox catalysis before nickel became popularized. The first account of transition metal and photoredox co-catalysis was in 2007 from the Osawa group, who used Rubippi and palladium in a copper-free Sonogashira. While today the field has expanded to include copper, cobalt, iron, osmium, and much more. In 2014, two important back-to-back publications in the field of nickel metallophotoredox chemistry came out from the Molander and Doyle-MacMillan labs, demonstrating a cross-coupling between BF3K salts and aryl bromides, and from the Doyle and MacMillan labs, two transformations, the decarboxylative arylation of amino acids and the alpha arylation of anilines. As you can see, we already have three distinct radical precursors that were successfully implemented, BF3K salts, carboxylic acids, and the proton alpha to an amine. In the interest of time, we will take a deeper look only into the Molander work. In their initial publication, they rationalized the mechanism as follows. The excited state photocatalyst, with an oxidation potential of 1.21 volts versus the 1.1 volt of the alkyl BF3K, is thermodynamically favored to undergo reductive quenching, thus oxidizing the alkyl BF3K to its benzylic radical. Meanwhile, in the nickel catalytic cycle, starting from a nickel zero source, nickel COD, oxidative addition into an aryl bromide will place the cyanoarine reactant partner onto the metal center. And from this nickel 2 species, the benzylic radical that was generated in the reductive quenching step can now engage the nickel complex, adding to it to furnish this nickel 3 intermediate, and now both reaction partners are on the metal. From this nickel 3 species, a reductive elimination event furnishes the desired product, as well as the nickel 1 species, which completes both the photocatalyst and nickel cycles by acting as an electron acceptor from the reduced photocatalyst. And if you look at the reduction potentials, we see that this step is thermodynamically favored, as the reduction potential of the reduced photocatalyst at negative 1.37 volts is more negative than that of the nickel 1 to 0 couple. While in their initial publication, they propose a nickel catalytic cycle involving alkyl radical addition to a nickel 2 species, later DFT studies suggested that an alternate mechanism is just as viable. Here, the alkyl radical generated in the photocatalyst quenching step adds first to nickel 0, giving a nickel 1 alkyl species, which then undergoes oxidative addition into the aryl bromide to provide the same nickel 3 species as proposed on the last slide. So both mechanisms converge with the nickel 3 alkyl aryl species. Additionally, in these DFT studies, the Molander group showed that the subsequent reductive elimination to give the product can be competitive with a simple dissociation pathway of the nickel 3 back to nickel 2 and a stabilized alkyl radical. As already mentioned, mechanisms for metallophotoredox chemistry are still being elucidated, and a significant body of work has emerged since 2015 on CC and CN bond-forming nickel metallophotoredox reactions, but they won't be covered here in the interest of time. It's also worth noting that in this study, as well as the Doyle-MacMillan paper, all three reactions developed utilize a bipyridine or BIPI ligand on nickel. Moreover, as you will see in the subsequent examples, they also make use of the BIPI ligand. BIPI, along with TERPI, BOX, PIBOX, just to name a few, are privileged ligands for one-electron nickel chemistry. This Trends in Chemistry review is a nice resource about ligands and nickel catalysis in general. The next concept I wanted to illustrate is the use of various radical activators, namely species that can abstract either a hydrogen or a halogen in order to generate the reactive radical species of interest. You will see two examples, one that uses a stoichiometric radical activator and a second that is catalytic. This example here illustrates the former, using a silyl radical to abstract the bromide from one of the coupling partners, thus enabling a cross-electrophile coupling. Mechanistically, this reaction is proposed to proceed by a very similar mechanism to the Molander chemistry that was just shown. We're using the same highly oxidizing iridium photocatalyst. This reaction goes via reductive quenching, oxidizing the bromide anion presumed to originate from dissociation of the nickel complex to a bromine radical. Meanwhile, in the nickel cycle, you see the same proposed reactivity pattern, an oxidative addition from nickel 0 to nickel 2, which gets the aryl coupling partner ligated on nickel, followed by addition of the key alkyl radical coupling partner to give the nickel 3 alkyl aryl species, which then undergoes reductive elimination to furnish the product. But the part that I wanted to focus on for this example is how this key tetrahydropyran radical is formed. This is where the silyl radical activation concept comes into play. The electrophilic bromine radical generated in the reductive quenching of the photocatalyst is well precedented to abstract hydrogen atoms from an SiH bond, which generates the silyl radical intermediate shown here. This silyl radical is then thermodynamically favored for halogen atom abstraction from an alkyl bromide. Compare the bond dissociation energy of an SiBr bond at 96 kcals per mole versus that of an sp3 carbon bromide bond at 69 kcals per mole for bromomethane. Thus, the tris-trimethylsilosilane, aka supersilane, acts as both an activator to generate the nucleophilic tetrahydropyran radical and the sacrificial reductant to balance this net reductive cross-electrophile coupling. I'd like to add as a final note that this particular transformation has proven empirically to be one of the most robust reactions and was one of the ones that was very rapidly adopted in industry. In the next example, we add yet another layer of complexity to the catalytic cycle. This example features a triply catalytic reaction, invoking both metallophotoredox and a catalytic radical activator to enable a direct CH alkylation of N-Bach-protected amines, forming a new sp3-sp3 carbon-carbon bond. Here, the proposed photocatalytic and nickel cycles are again quite similar to those from the previous examples. One of the reaction partners, the alpha amino radical of N-Bach-pyrrolidine, adds to nickel 0, and then this is followed by an oxidative addition of the other alkyl bromide coupling partner to access the key nickel 3 species, from which reductive elimination furnishes the product and a nickel 1 species that is then reduced by the photocatalyst back to nickel 0. With respect to the photocatalytic cycle, the key difference is that from the excited state, the photocatalyst is actually not oxidizing enough to directly oxidize the N-Bach-pyrrolidine substrate. However, it is thermodynamically favored to oxidize this amine organocatalyst, quinupridine. From here, the radical cation of quinupridine, an electrophilic radical, can selectively abstract an H dot from the alpha proton of N-Bach-pyrrolidine in order to access the key alkyl radical coupling partner. And meanwhile, a simple deprotonation of the quinupridinium will recycle the HAT catalyst. These classes of reactions, termed indirect HAT photoredox, are incredibly useful for accessing certain radical species that the typical photocatalyst may not be able to directly furnish because, as seen here, they're either not oxidizing or not reducing enough. The use of a separate HAT radical activator opens up the range of accessible radical intermediates. This example uses quinupridine, but there's a plethora of radical activators that have been used, and the review listed here at the bottom gives a nice overview of various carbon, nitrogen, oxygen, and sulfur-based radical activators. The final example from this section deals with a complementary type of photoredox reactivity, termed direct HAT catalysis. In this case, an excited photocatalyst will directly act as an HAT catalyst instead of performing a single electron transfer. This reactivity is special because it opens the door to activation of unactivated alkyl CH bonds, the holy grail of CH activation chemistry. To illustrate this type of reactivity, we will look at Alison Wendland's epimerization of methine stereocenters, which is done using a decatungstate photocatalyst, an inorganic polyoxometallate or POM derivative. Such POM derivatives have been described to engage in HAT reactivity of inert alkyl CH bonds since the 1980s, with pioneering work from Craig Hill. But for this lecture, I've decided to go with a very recent example from the literature because it showcases the potential of this reactivity paradigm, the ability to perform late-stage epimerization on advanced intermediates. Like with the ruthenium and iridium photocatalysts, we begin with excitation, except with these decatungstate photocatalysts, their excitation maxima is 324 nanometers, thus necessitating the use of UV light. Upon excitation, the decatungstate will undergo a ligand-to-metal charge transfer, initially entering a short-lived singlet excited state that relaxes to a presumed long-lived triplet excited state, which is the actual reactive species. This triplet species has a reduced tungsten metal center and a partial O-centered electrophilic radical character, making it good at abstracting hydridic CH bonds. Thus, in the presence of a substrate such as this cis-1,2 disubstituted cyclobutane, the methine hydrogen will be abstracted to furnish the protonated monoreduced form of the decatungstate catalyst and the key alkyl radical species. A disulfide co-catalyst that homolytically cleaves to give a thiol radical helps to return the decatungstate photocatalyst to its ground state, and the resulting thiophenol then serves as the H dot source to furnish the desired epimerized thermodynamically favored product and to regenerate the thiol co-catalyst. As a disclaimer, this mechanistic cycle was not explicitly spelled out in the publication, thus represents just my best guess at how the reaction is proceeding based on previous publications from the Wendland lab and similar decatungstate photoredox transformations. This brings us to the end of this second section. There's a large body of work in both the indirect and direct HAT fields, with many chemists that should be credited: Wu, Ravelli, Sorensen, Glorious, Rovis, and many more. There's also a related but distinct field of proton-coupled electron transfer, or PCET, which I didn't have the time to cover, but is also a very important topic. Thus, I've listed 2 reviews from the field. The second, which is quite the magnum opus at more than 250 pages, comes from the Knowles Lab, a huge contributor to the area of PCET photoredox catalysis. And this review provides a comparison of PCET in photoredox and electrochemistry. But now we move on to the last section, being able to design your own novel photoredox-based reaction. And we'll start with one of the most important parts, choosing the right photocatalyst. For orientation, on this chart at the bottom, the more reducing or negative values are going to be at the right, while the more oxidizing or positive values are going to be more on the left. Earlier in the lecture, I used ruthenium polypyridyl photocatalyst to illustrate photophysics. Now for a change, I'm going to use iridium-based photocatalyst to illustrate the concept of redox windows and how to tune them. Shown here is an iridium trisphenyl pyridine or iridium PPY3 photocatalyst, one that is known to be highly reducing. Its placement on the chart at negative 1.73 volts represents the excited state reduction potential for the photocatalyst to reduce an acceptor substrate in an oxidative quenching mechanism. Again, all of the values here and on subsequent slides are going to be versus the saturated calomel electrode and are measured in acetonitrile. After the excited state photocatalyst reduces an acceptor substrate, it will now be in an oxidized iridium-4 ground state. This oxidized ground state has a specific oxidation potential in order to recycle it back to its iridium-3 ground state. And the placement of this catalyst at left here represents this oxidation potential of plus 0.77 volts. Thus, from minus 1.73 volts to plus 0.77 volts is considered to be the redox window for the oxidative quenching mechanism for this catalyst. Of course, this catalyst also has a reductive quenching redox window, corresponding to a window between plus 0.31 volts, the oxidation potential of the excited state photocatalyst, and negative 2.19 volts, the reduction potential of the reduced ground state photocatalyst. So by now, it should be clear that the 4 values listed under the catalyst correspond to the excited state quench redox potentials, as well as the potentials for either the oxidized or reduced ground states. So this slide shows the values for iridium PPY3, but there's actually a larger chart that was created by Merck and the MacMillan group that lists some of the most common ruthenium and iridium photocatalysts and their 4 redox potentials. And this can be found on the MacMillan group webpage. So the big question is, how would you modify this redox window if it wasn't right for the substrates you're working with? To understand this, we need to first understand what parts of the photocatalyst are responsible for reduction and which are responsible for oxidation. Here are the locations of the HOMO and LUMO of an iridium homoleptic catalyst, homoleptic meaning all the ligands are the same. So upon excitation, which involves the metal to ligand charge transfer, based on the location of the LUMO, it means that the excited electron from the metal center will primarily be localized on the pyridine part of the ligand. Therefore, the pyridine moiety has the highest impact on the excited state photocatalyst reduction potential, logical since this is where the concentration of electrons is, while the phenyl moiety is going to have the highest influence on the oxidation potential. In other words, if from iridium PPY3 you wish to make your photocatalyst more reducing, add electron donating groups to the pyridine moiety, and if you want to make it more oxidizing, add electron withdrawing groups to the phenyl, which will serve generally to withdraw electron density from the metal center. We're going to see this played out in this particular decarboxylative arylation example, which basically requires an oxidation of N-Bach proline and a reduction of a cyanoarine partner. We start here with iridium PPY3, the first catalyst the authors tried. On the chart at the bottom, I've also marked out the oxidation and reduction potentials of N-Bach proline and the 1,4-dicyanobenzene substrates respectively. So you'll see that while the excited state photocatalyst has a reduction potential of negative 1.73 and is thermodynamically favored to reduce the dicyanoarine at negative 1.61 volts, the same is not true over here with the oxidation of the N-Bach proline substrate. Here the oxidation potential of plus 0.77 volts is endothermic relative to the substrate. So we need a catalyst that is as reducing as iridium PPY3, but more oxidizing. The information on the last slide will tell you to add electron withdrawing groups to the phenyl moiety of the ligand. And that's exactly what they do. They test a photocatalyst with a fluorine substitution on the phenyl, which indeed pushes the oxidation potential now to plus 0.97, making the oxidation slightly exothermic. However, this catalyst is not ideal due to the fact that its redox window is more or less exactly matched to the reduction and oxidation potentials of the substrate. And ideally, you'd like a slight overpotential. So let's see what happens when they try to add 2 fluorines to this phenyl moiety. With 2 fluorines now, you do get an overpotential for the oxidation event. Compare plus 1.13 volts to the plus 0.95 volts of Mbach proline. However, on the reduction side, you're now endergonic. So how do they adjust for this scenario? They add electron donating groups to the pyridine moiety to recover some of the reduction power. Now, with a tert-butyl substituent on the pyridine, we finally arrive at their optimal catalyst, which has a slight overpotential for the reduction. And while the paper did not mention the exact oxidation potential for this catalyst, presumably there is also a slight overpotential as well for oxidation. So these changes allowed them to optimize their yield from 12% using iridium PPY3 to 68% with this final optimized photocatalyst under identical conditions. Then further changes to the base brought the yield up to 83%. So now what about for heteroleptic catalysts? Heteroleptic meaning where the 3 ligands are not all the same. The concept is the same, but the HOMO-LUMO locations are different. The LUMO lies on the more electron-deficient BiPi ligand, meaning after the metal-to-ligand charge transfer, the electron will be localized on the BiPi, meaning this is the moiety that will be dictating the reduction potential, while the moieties that drive the oxidation potential will be the phenyl rings. Additionally, between the homo and heteroleptic photocatalysts, the heteroleptic ones are universally going to be more oxidizing due to the presence of the more electron-deficient BiPi ligand, which reduces the electron density on the metal center. So with these factors in mind, if we now look at these 3 common iridium photocatalysts, we can rationalize their relative excited state redox potentials. We have the popular iridium DFCF3 PPY diterbutyl BiPi catalyst as the most oxidizing, due to the dual effect of the BiPi ligand withdrawing electron density from the metal center, as well as the presence of the difluoros on this phenyl moiety. Then less oxidizing will be that same catalyst but without the difluoros. And finally, you have iridium PPY3 as the least oxidizing. Conversely, looking at the right-hand side now, with respect to excited state reduction, iridium PPY3 as the sole homoleptic catalyst is the most reducing. And you'll notice that the difference in reduction potential between these 2 heteroleptic catalysts is very similar, which makes sense due to the fact that the moiety controlling reduction, the BiPi ligand, is the same between the 2 catalysts. Again, the MacMillan photoredox chart will provide these redox potentials and those for several more catalysts. Check out the references here below for even more comprehensive studies of iridium photocatalysts. Finally, the MacMillan photoredox chart also provides the potentials for common organic substrates. I find this is a nice resource for designing new reactions to help figure out how to close your catalytic cycles, if not directly with the coupling partners themselves, then via an intermediate species like the radical activators that were mentioned earlier. Hopefully after this exercise, if you have an idea for a new photoredox transformation in mind, you will now know how to both choose or design your photocatalyst, and also close the catalytic cycle by guaranteeing a small overpotential in the direction that you need. Now, let's say you manage to find some new reactivity, and now you wish to understand better what's going on in your reaction. One of the simplest mechanistic studies is to do a SternVUlmer Quenching study. This study answers one simple question: is there a reaction between the excited state photocatalyst and a specific substrate, officially termed the quencher? This graph represents the fluorescence intensity of the excited state photocatalyst in the absence of a substrate. Now say the substrate does quench the excited state. Then what you would see is that with increasing concentration of the substrate, the fluorescence intensity of the photocatalyst will decrease. And this can be plotted to yield a linear response of the radiative quantum yield versus the concentration of the quencher. There are actually 2 different types of quenching a SternVUlmer study can detect: dynamic quenching, which is based on collisions between the quencher or substrate and the excited state photocatalyst, and static quenching, which occurs when you have, for example, pre-association between the catalyst and quencher. However, to distinguish between these 2 types, you'll need to run a SternVUlmer in addition to other methods, which won't be discussed here. It's important to stress again that SternVUlmer will only tell you if the substrate you're analyzing quenches the excited state of the photocatalyst. Not only will it not distinguish between reductive or oxidative quenching, it will also not distinguish between quenching via energy transfer, which was the other mechanism under the broader umbrella of photophysics. It's also important to know that oxygen is known to quench excited state photocatalysts via energy transfer, meaning if you have residual oxygen in your SternVUlmer setup, you can be misled to believe that the substrate you're analyzing is quenching, when in fact it's just oxygen. As a side note, Timothy Noel's group from the University of Amsterdam has developed an automated SternVUlmer method in flow, which keeps the system closed to prevent oxygen exposure. So how does one tell the difference between single electron transfer and energy transfer, and furthermore between reductive and oxidative quenching mechanisms? For this, you will need transient absorption or TA spectroscopy. In this talk, I will not go into detail in this method, but the review cited at bottom is an excellent resource if you're new to TA spectroscopy. In very simplified terms, TA spectroscopy uses a laser pulse to excite a sample, while a white light sample assesses the absorption of the excited species. It measures the difference in absorption between the excited and ground state, with two wavelengths assessed, that of the lambda max of the oxidized metal and the lambda max of the reduced ligand. And in short, tracking both these wavelengths and comparing them to the TA trace in the presence of no quencher, you will be able to distinguish between the various possible quenching mechanisms. In these graphs, you're looking at the change in absorption from the excited state to ground state, that's your y-axis, over time, your x-axis. So when the graphs reach zero, this indicates a full relaxation back to the ground state. An energy transfer mechanism is indicated by full relaxation back to the ground state at both of the assessed wavelengths at the same rate, since in an energy transfer mechanism, both the oxidized metal and the reduced ligand species are lost simultaneously upon quenching. Whereas with reductive or oxidative quenching, depending on which it is, you will not observe full relaxation back to the ground state in either the lambda max of the oxidized metal or the lambda max of the reduced ligand. Next, we will address some common troubleshooting in developing your own photoredox reaction, or address some aspects you should always keep in the back of your mind with this type of chemistry. The first big one is the fact that back electron transfer, a process where after the photocatalyst is quenched, say it reduced a substrate, that reduced substrate does not manage to leave the solvent cage of the photocatalyst before giving back the electron it just gained from the photocatalyst. Back electron transfer is always possible, thus solvent screening is a large part of reaction development, because the solvent can make a significant difference in mediating BET pathways. Another important factor with multi-catalytic reactions is to bear in mind that it's important to match your catalytic cycle rates, which you can tune by adjusting the individual catalyst loadings. For example, if you're developing a metallophotoredox coupling with an aryl bromide coupling partner, and you observe large amounts of proto-dehalogenation, it could be indicative that the nickel cycle is faster than the photocatalyst cycle. Thus, one cycle is simply churning through substrate, waiting for the other to catch up. Another classic problem is light penetration. It is well established that with blue light, light penetration only goes at most a few millimeters deep into your reaction vessel. The penetration depth can change depending on light source. For example, red LEDs and infrared light will penetrate deeper. But with the most commonly used blue light photoredox reaction, maximizing the surface area of your vessel and minimizing its thickness is an important parameter in reaction efficiency. Hence why flow setups have a lot of traction in this area. Now the last topic of this section, the reaction setup. This slide will use pictures to illustrate the evolution of photoredox setup design, starting with the use of CFLs in the early days, so circa 2008-2009, and then moving to the use of blue LEDs once we realized it was more efficient to deliver light that closely matched the absorption wavelengths of these photocatalysts. However, the blue LEDs had their issues. Namely, the lights generated a lot of heat, and due to the already mentioned light penetration issue, you could only put 2 vials in front of one light, meaning each vial received quite a lot of light intensity, and reaction solutions could easily heat up to 45 degrees Celsius. Then came the PEN reactor, a fully integrated photoredox reactor with built-in fans for efficient cooling, mirrors for maximized light exposure, and covers for the blue LED light. And now, we also have custom-made HTE plates with holes from the bottom for light penetration, enabling chemists to optimize photoredox reactions in HTE format. Finally, a huge research area is photoredox and flow, again really to maximize the light penetration in the reaction vessel. And with that, we come to the last topic, and just one last slide of content, a quick look at some current trends in the field. Some of these trends you will have seen or I have alluded to already, for example, expanding beyond iridium and ruthenium-based photocatalysts with different end goals. In this highlighted example from the Rovis lab, the use of an osmium photocatalyst switches the light source from visible to near infrared. for excitation, which greatly increases the catalytic efficiency as the strong spin-orbit coupling of osmium photosensitizers allows for direct excitation from the ground state to the triplet state without first going through a singlet excited state. Moreover, near-infrared light has the advantage of being far more penetrant than blue light, which addresses one of the largest practical issues with photocatalyst reaction design. There are also many examples employing base metal catalysts such as iron and cobalt, which has the added advantage of moving away from expensive and rare earth metals like ruthenium, iridium, and osmium. And while the use of organic photocatalysts is not by any means new, as organic dyes have been used in this modern era of photoredox chemistry almost as early as the metal polypyridyl photocatalyst, it always remains a trend due to the fact that they are green and don't use transition metals. This review from the Nicewicz lab is an excellent resource to see all of the classes of organic photosensitizers. The technological innovations, you already saw a flavor of them on the last slide with the advent of HTE for photoredox screening and a laboratory flow setup. But new designs are constantly being developed and is a really large research area. And this review at the bottom from the Noel group really gives an excellent flavor of various reaction setups in flow and for HTE. Finally, a blooming area is the bimolecular homolytic substitution, or SH2 manifold. The basis of this reaction manifold is to control the selectivity of reactions involving alkyl radicals by having a catalytically generated alkyl radical bind with and thus be stabilized by a metal complex long enough for another catalytically generated alkyl radical to displace the metal via singlet SN2 type displacement. This new manifold is seen as a way to overcome the intrinsic lack of selectivity for sp3-sp3 cross-coupled products due to non-selective radical recombination. This brings us to the end of this special topic lecture. Photoredox catalysis has really exploded as a field, so the content covered here is by no means comprehensive, but hopefully provides a good starting point. Thanks so much for watching.
Thank you, Tracy, for an outstanding talk, which really gives a great overview of the field. In our next episode, we'll continue with this module. See you next time!